Good morning, friends. Today we are going to analyze problems using square potential barrier. I have taken two problems from Aruldas. The first problem, it is given that an alpha particle is trapped in a nucleus of radius 1.4 into 10 raised to minus 15 meter. We have to calculate the probability that it escapes from the nucleus if its energy is 2 MeV. Energy is given as 2 MeV, and the potential barrier at the surface of the nucleus is also given, that is V0 4 MeV, and mass of alpha particle is also given 6.64 into 10 raised to minus 27 kilogram. This is all the values are given. We can directly substitute the values. See, radius is given, so A is actually diameter. Diameter will give the value of width of the barrier, so twice 1.4. That will give the width of the barrier. So now we have all the values. By substituting, we will get 0.124, or it is 12.4 in percentage. Similarly, for the second problem also, all the values are given. Here it is mentioned that width of the barrier is 2 angstrom. So we need not take twice the given value, because width is directly given. So A is directly given as 2 angstrom. Again we can substitute it directly. Energy of electron is given, potential barrier is given, width is given. So, and the mass of electron is known. So substitute all the values. Again, in a similar way we can calculate. The answer will be 0.085. 0.085. In percentage, it is 8.5%. We have to show that the energy and wave function of a particle in a square well of finite depth V0 reduces to energy and wave function of a square well with rigid walls in the limit V0 tends to infinity. So from the theory and basic conditions of solutions of Schrodinger equation to square well of finite depth, we have this condition: Ka into tan Ka is equal to alpha A. Cancelling A, we have tan Ka is equal to alpha by K, where alpha and K takes the values. While we were deriving or writing the Schrodinger equation, we have identified alpha and K like this. So substituting the values of alpha and K, we have tan Ka is equal to square root of V0 minus E divided by E. Now we have to apply the condition that limit V0 tends to infinity, tan Ka. That means if this one tends to infinity, if we rewrite this one by dividing by E, we have V0 by E minus 1. That means if V0 tends to infinity, tan Ka will be tending to infinity. For tan Ka to tend infinity, Ka should take the value of n pi by 2. As you know, tan Ka is sine by cos. Sine n pi by 2, sin pi by 2 will be maximum and cos pi by 2 will be 0. So 1 by 0, that means it tends to infinity. So we have Ka is equal to n pi by 2, squaring and applying the value of K square, we have energy eigenvalue as that of infinite square well potential. So infinite square well potential can be determined as a limit of finite square well potential. When V0 tends to infinity, square well of finite walls tends to infinite square well. So we have the corresponding energy eigenvalue. Let us also check how the wave function changes. So we already have wave function of finite square well of depth V0. So because it is mentioned in the question that we have to find the limit V0 tends to infinity. When we apply V0 tends to infinity, correspondingly we will have alpha tends to infinity, because we have alpha square is equal to 2m by h cut square V0 minus e. That means when V0 tends to infinity, alpha tends to infinity. That means e raised to alpha x means this tends to infinity. That is not an acceptable form of wave function. So we take it as we neglect it, that is 0. Here also we have a infinite value, so we neglect that case. Here also we have 0. The only possible value is this one, so we change the coefficients, that is a sin kx plus b cos kx. This is the eigen function in the case of infinite square well potential, like we have eigenvalue in the case of infinite square well potential. So now we have infinite square well potential eigen function and eigenvalue by applying limit V0 tends to infinity in the case of square well of finite barrier. So it is an approximation. Square well of infinite barrier is an approximation of square well of finite barrier in the limit V0 tends to infinity. Given is normalize the wave function hn of y e raised to minus y square by 2. We know that it is the wave function of a linear harmonic oscillator. So in order to normalize, we apply a constant n. So this is our condition of normalization. So apply the values nn star hn star e raised to minus y square by 2 into nn hn e raised to minus y square by 2. So only nn will have nn star nn, the other will be just squared. So hn square e raised to minus 2y square by 2. That means it is e raised to minus y square. Now dx. In the derivation we already have a conversion factor like y is equal to square root of m omega by h cut into x. So taking the differentials, we have dy is equal to square root of m omega by h cut into dx. Substituting the value of dx, we will have the parameter, the variable in terms of y. And take this constant also outside the integral. So this integral actually gives the orthogonality property of Hermite polynomial. This integral is known as the orthogonality property of a Hermite polynomial, and the solution is given like this, that is square root of pi into 2 raised to n into n factorial. So we directly give that value. We have the right hand side is equal to 1 because it is the normalization condition. Taking all the constants to the right hand side, we have mod n square is equal to square root of h cut by m omega square root of pi 2 raised to n factorial. So rearranging it, we have square root of m omega by pi h cut into 1 by 2 raised to n factorial. This is n square, so n will be all raised to 1 by 2. So we can rewrite the value of normalization constant in the Eigen function of a linear harmonic oscillator. Now we have to calculate expectation of x and expectation of px for the nth state of linear harmonic oscillator. So I have written the wave function in terms of y, and it is converted to x in using the conversion factor. Y is equal to square root of m omega by h cut into x. So we have psi n of x here. So we usually use this form of a wave function, that is in terms of x. So let us write expectation of x. So for easiness of writing, I am writing n square because n star n we have, and x actually what we do is psi n star x psi n integral dx. So from psi n star we have n star h n of x e raised to minus m omega by 2 h cut into x square, then x, then again from psi n we have one more n h n of x e raised to minus m omega by 2 h cut into x square. So this is 2 times m omega by 2 h cut into x square. So we will have m omega by h cut, and here we have 2 h n of x, so h n square. Okay. So whenever we use the expectation value, we have to sandwich the operator between psi star and psi. So that is what I have done, and n star n is taken outside. Now we have x h n square e raised to minus m omega by h cut into x square dx. So using the property of because Hermite polynomial is involved, using the property of Hermite polynomial, we can write this integral as a 0 because it is an odd function. So expectation value of x is 0. We can also calculate expectation value of px to be 0. Still we have to show the minimum calculation. Yeah, I have written the expectation value of px. Again n square is taken outside. H n of x e raised to minus m omega by x 2 h cut into x square, then operator I minus I h cut d by dx is kept between psi star and psi. Now here we have d by dx, that means it is like d by dx operating on this wave function psi n of x. So we have to find the differential, that means we have to consider differentiation by parts because we have 2 terms. First h n prime of x into exponential, then h n of x into differential of the exponential term. Differential of the exponential term gives this into minus m omega by 2 h cut into into x square is 2x. Even though we have differentiated it, again will have the same odd function property turns out. That means the integral of both the terms will be 0. This is also not going to exist.